Finally, I'm going to talk quickly about expectation for this part of the lecture on solidification and homogeneous nucleation slash heterogeneous nucleation from liquid. Okay, the first one is about understand the homogeneous and heterogeneous nucleation, including the physical meaning of each of the terms, such as the driving force, the barriers, the size, and the similarity and the difference between homogeneous nucleation and heterogeneous nucleation. Homogeneous, of course, meaning the nucleation behavior is happening uniformly, randomly throughout the liquid melt, while heterogeneous nucleation is happening at a specific location, such as on the mold wall. Okay, and the driving force is the same. The barrier uh, driving force is fundamentally the same. It's the reduction of the volume-free energy, while the barrier is the creation of the uh, interface and associated interfacial energy. And one has to overcome the barrier in order for the nucleation process to occur. Okay, and that only occurs favorably under certain undercooling condition. And I also expect you to be able to derive the so-called critical nuclear size. If it's for a sphere, that means radius, but for some other geometry, you may have different dimensions, such as edge length for a cube, and the critical nucleation energy for simple geometry for homogeneous nucleation. I want you to be able to derive the simple nuclear size by considering the change in Gibbs free energy during the nucleation process, what is driving it, and what are the barriers. And you get the so-called first derivative with respect to the free energy change versus the critical dimension, for example, the radius. I also expect the students to be able to understand the physical meaning of critical nuclear size, the critical nucleation energy or nucleus barriers for both homogeneous nucleation and heterogeneous nucleation. The critical nucleus size is kind of the critical size smaller than which, if there's such a cluster, that cluster has a tendency to disappear, to melt back into liquid. Well, if the cluster size is larger than this critical nuclear size, then that cluster has a tendency to grow, continuous grow, and from that point, the free energy change would be always downhill, always spontaneous. The nucleation barrier is kind of the energy barrier that in order for the nucleation process to happen. And the higher the barrier means the lower the probability you have to wait for longer for a certain part to become a solid nucleus. And the lower the barrier means the nucleation process higher probability to happen. Okay? And generally, with respect to undercooling, the larger the undercooling, the smaller the nuclear size, the lower the nucleation energy, the lower the barrier. On the other hand, the smaller the undercooling, the larger the critical size or the higher the barrier. Okay? I also expect students to be able to understand the change of critical nuclear size. The uh, largest nucleus cluster size and the nucleation rate in supercooled liquid with respect to undercooling, which I just quickly mentioned a little bit. The larger the undercooling, the smaller the critical nuclear size, or that critical value when the um, the the first derivative of the Gibbs free energy change with respect to radius is zero. The slope is zero. The largest cluster size is the largest kind of local region within the liquid that is arranged like a solid, like a crystal. And that one increase mildly with increasing uh, undercooling. And the nucleation rate typically when the undercooling is relatively small, the nucleation rate is essentially zero. But beyond a certain region, the nucleation happens dramatically. Nucleation rate goes up tremendously when the undercooling goes beyond a certain level, goes higher than certain level. I also expect students to be able to understand the growth of pure solid after nucleation, including the major types of uh, growth mechanism. Okay, and also understand the impacts of temperature gradient on the stability of the growth front. For example, we are talking about planar growth versus lateral growth. Okay. In addition, I also expect students to be able to understand the three simplest scenario for a solidification of an alloy instead of pure element. For alloy, we said that's the equilibrium solidification when you cool extremely patiently, extremely slowly, and wait for the composition to reach equilibrium. Okay, by even though it means slow diffusion. The second scenario is the one that you have stirring in the liquid, but at the same time, um, there's no diffusion in the solid. And the last one is when you do solidification, when you uh, do not have. And the third one we mentioned is no diffusion in the solid and the diffusion mixing in the liquid phase. Okay, and for each of them, how do we understand the local composition change um, over time? And I also expect you to understand the concept of constitutional supercooling in liquid, which is very important for many applications. The supercooling or the temperature of the liquid is lower, not than the solid, but than the equilibrium temperature as determined by local composition due to the slow diffusion even within the liquid. Okay, and another concept that I want you to be able to understand is the formation of different zones during casting. For example, the chill zone, the column zone, and the equiaxed zone during casting. When each of them form, for example, the chill zone is due to the coldness. When you pour liquid into a hot mold, and right when the liquid meets the cold mold wall, there's a large undercooling and a lot of defects. You form equiaxed small grains, and after that, it slows down, become column growth because at that time the solidification is controlled by heat conduction, and towards the end when the column zone starts to meet each other and deep within the liquid, um, the branches fell off and they would form equiaxed dome because they would interact with each other and can no longer sustain the linear growth. In that case, we will have equiaxed zone again. And I want you to be able to understand these phenomena and do some simple explanation. Okay?